In this video, we're going to look at some nuances, I guess, some more details about chair structures. Instead of worrying about their depiction, what are some ramifications of chair structures, that sort of thing, some analyses that we can do with chair structures. And so, getting into it, what we want to introduce is a new topic that's called 1-3 diaxial interactions. 1-3 diaxial interactions. This is a fairly simple concept, but if you understand chair structures, it's a fairly simple concept, but the actual term is kind of awkward with this 1-3. And even once you understand the concept, the 1-3 still have trouble making sense. But anyway, let's get into it. So what this allows us to do is determine the relative stability of chair structures. And in particular, it's chair structure conformational isomers. Sorry. So chair structure conformational isomers, this is just chair flipped structures. So when two structures are, we have kind of two structures, and the way they differ is a chair flip. That is me just saying the chair flip. Another way of saying that long is to say that they're conformational isomers of each other. So for example, if we look at methyl cyclohexane and we convert this to a chair, to do this, we first draw our favorite chair. I'm going to draw this one. It actually would be kind of helpful if you drew the same one. And then I'm going to add the methyl group. I can pick any position I want. There's no wedge or dash, so I can make it pointing up or down, that sort of thing. I'm going to just choose to have it pointing up as an equatorial substituent at the furthest right carbon. And then what I want to do is I want to flip this. Now when we flip a chair, we flip both the flaps. Now, if we have a methyl group at the furthest right carbon of our original chair structure, it needs to be at the furthest right carbon at our final chair structure. Now, instead of being equatorial, this group is going to be axial. It still retains its up position, its upness, I guess, but to determine, but it's now axial instead of equatorial. Okay, so we have our two chair structures, and I show equilibrium arrows. And this is the sort of conformational isomerism. That is, the conversion of these two isomers occurs as a result of chair flipping. And these two structures are chair flipped versions of each other. You could say that. A more precise term would be they're conformational isomers of each other. Okay, so my question is, which is preferred? And for those of you that have a deeper chemistry background, I would say which is preferred at equilibrium. Now, the answer to that question is the more stable, excuse me, I want to write more here, more stable isomer. So the more stable isomer is preferred at equilibrium. And in this case, between A and B, it is A. Now, the reason why, we could ask, why is A preferred at equilibrium? What we could do is invoke our understanding of something called 1-3 diaxial interactions and say 1-3 diaxial interactions are minimized want to see that structure. When the methyl group is equatorial, one,3 diaxial interactions are minimized when the group is equatorial. Those are kind of the big takeaways from this, okay? Now I realize I haven't told you what 1,3 diaxial interactions are, and I will show that on the next slide, but if you want to, really all you need to know is that groups prefer to be equatorial. And if you know that, you should be able to kind of solve any question where I pose to you two structures, they're conformational isomers or chair-flipped versions of each other, and I ask you which is more stable. So the methyl group is, the group is equatorial, allows for the molecule to be more stable. So 1,3 diaxial interactions. Kind of avoiding this because the name is just so awkward. 1,3 diaxial interactions are, these are sort of, well, let's just say it this way. When a group is axial, well, that doesn't need quotes, but the next word does. When the group is axial, it will bump, there we go, that one needs quotes, it's awkward, but it gets the job done. It will bump into the other axial substituents. And those other axial substituents are most often hydrogen atoms. Sometimes they could be other things, and when they're other things, it becomes an even bigger deal. So most often we're talking about hydrogen atoms. So what am I talking about here? Well, I want to consider the first structure, or excuse me, actually, in these notes, I want to consider structure B. So we're going to look at this structure, structure B. So I'm just going back here, going to redraw that, which means I have drawn the wrong chair structure. Sorry. Okay, so this was structure B. I'm considering structure B because we have a methyl group, which I could even write as my CH3, positioned axially, which means we're going to see 1,3 diaxial interactions. I wish they just termed this diaxial interactions, but they don't. Okay, so we have the CH3 drawn axially. Now I'm also drawing the hydrogen atoms that are axial and on the same face. Now what's happening is these groups are sort of seeing each other in space and bumping into each other. And so the CH3 is feeling the effect of being nearby the other two axial or diaxial substituents, which are hydrogens in this case. So the CH3 bumps into the 2, that's where the di comes from, axial groups on the same face. Okay, I realize that there are 3 axial substituents that I'm not drawing here on the opposite face. The CH3 is too far away from those axial substituents to feel this effect. So we have our diaxial interactions. So these two groups axial groups are interacting with the CH3. And that's where I'm saying bumping into. Another term we would say is steric hindrance is occurring. I've done too many of these videos to recall if I've defined steric hindrance. So I'll do that again down below where I'm saying steric hindrance is basically saying that groups want to avoid each other in space. Unless there's some sort of electronic attraction. And my physics friends would prefer if I said electrostatic. So unless there's some sort of attractive force between two atoms or two groups, whenever these things are positioned close to each other in space, they will want to avoid each other, and that's what steric hindrance says. Again, I may have defined that previously. Okay, so we have our diaxial from the name 1,3 diaxial. We have the interactions, which comes from steric hindrance. We don't really have this number 1,3. Well, what it's saying is that if you numbered one of these substituents, our substituent that, or let's number the methyl group, okay? So if we number the methyl group as position 1, we would be interacting with that methyl group 3 atoms away or 3 bonds away. So it's a bit awkward. So however you want to count it. What we're saying is that the 2 hydrogen atoms that are on the same face and that are also axial are either 3 bonds away from that methyl group. Well, I guess not even 3 bonds. It's 3 atoms. It has to be. Yeah, so we have 1, 2, 3 atoms away are the interacting groups. And you could go in either direction. So 1, 2, 3, starting from the methyl group, getting to the hydrogen that's interacting. And another thing you could, yeah. And so the numbering is a bit awkward. If you call this diaxial interactions, I would be fine with that. It's just that in the textbooks, they call this 1,3 diaxial interactions. Anyway, what it is it's steric hindrance, big groups bumping into each other, which is bad if they're not attracted by some sort of electronic interaction. It's big groups bumping into each other in a very predictable manner. That is, it's always, if you've got an axial group that's big, we are going to feel the effect of interacting with the other 2 axial groups on the same face that happen to be 3 atoms away just by the nature of chair structures. Okay, so hydrogen atoms provide some sort of interaction, and it turns out that we could have something a bit more complicated. Like, let's say that we've got some bigger groups. When multiple groups are on the ring, the largest group will prefer to be equatorial. Now, let's look at some examples of that. So my go-to big groups in this class, let me back up a second. So steric hindrance is a really important topic in organic chemistry. So understanding when you see a large group present, you want to try to minimize steric hindrance. That is the opportunity for that big group to interact with other things in the molecule. What I like to do is pick on 2 big groups in particular. When you see these things, just assume they're big groups. Are there bigger groups out there? Sure. Are they sometimes, is that important? Maybe. The important thing right now is I don't want you to worry about, hey, is it big enough or is it kind of medium size? We'll just assume that these 2 groups I'm about to show you are just big. Anytime you see them, you assume that they're big, and you're going to try to take this topic that we're talking about, steric hindrance, and try to minimize it in whatever way we're talking about here. So in this case, it's 1,3 diaxial interactions. So my big groups are something that looks like a chicken foot here, and this thing that looks like a Y. Now recall these are just bond line structures. So this is actually a 4-carbon unit in the first case with 3 methyl groups hanging off of it, and then and then the next one is a 3-carbon unit requisite hydrogens are assumed to be there. This first group is called tert-butyl. The next one is called isopropyl. So hopefully you can recognize the butyl and the propyl meaning. We have 4 times carbon for the tert-butyl group, and we have 3 times carbon for the isopropyl group. And sometimes these are just abbreviated as lowercase I than PR, or lowercase t and BU. And if you can really draw it well, the I and the T in these are italicized. Okay, so what I'm saying is that these are groups that could be attached to a ring. And so between these two groups, you would say this is big, this next group is not big, but it is bigger than C, or excuse me, bigger than H. Okay, so the tert-butyl group, if you see it present on a ring, you assume that it's the big group. And when we're looking at something like 1,3 diaxial interactions, you'll want to think about it as the big group. That is something that we prefer to be equatorial. Now, is this fair if I put, is it fair if I put both the isopropyl and the tert-butyl on the same ring? The answer is no. I don't want you to worry about a tert-butyl and an isopropyl, one being bigger than the other. Okay, it's just not worth it. So we just assume that they're both big groups, and I wouldn't put them both on the same molecule unless they were like working together or something. But even though the tert-butyl group has an extra methyl group, that doesn't always mean it's that much bigger. Okay. So I'm, for the most part, going to put methyl groups, tert-butyl groups, and isopropyl groups on cyclohexane rings and ask you to draw chair structures and tell me which one is preferred or not. That is, you probably want to put the one that has the big group equatorial. So again, to recall, 1,3 diaxial interactions. Larger groups want to be equatorial. That's really the takeaway. Now, there's a deeper definition where I say something like, when two chair structures are conformational isomers of each other by chair flipping, at equilibrium, the preferred chair flip geometry is going to be one that positions the larger groups to be equatorially. And the way these things work is that hydrogen is less than CH3, which is less than tert-butyl or isopropyl. So we have our two big groups. In between that is CH3, and then last but not least is hydrogen. And these are the only groups I would throw at you. Anything else where you're like, ooh, is an ethyl group is smaller than a tert-butyl, right? Well, let's just not even get into it. That's not what I'm trying to test you on. Okay, so the task is then, if we have a molecule like this, I want to, one, draw both chair structures. Or the conformational isomers of them. So you draw one and then you do a chair flip. Step 2, indicate which is preferred at equilibrium. So indicate which is preferred at equilibrium. Okay, let's do this. So I'm going to first draw a chair structure that I like. Okay, that passes the sniff test in terms of a high enough quality chair structure to roll with. Maybe you even want to just go ahead and draw your equilibrium arrows and show the chair flipped structure. Okay, now we're going to add groups. So we've got like a starred carbon and then maybe a squared carbon that we're going to add our two groups. And so maybe I will assign the leftmost carbon the star, and then going around the ring, it doesn't matter which way, but clockwise, this way is the same as going from here to here to here. We're going to go 2 carbons away just across the ring to the squared carbon. So those are my 2 carbons. I'm going to then add where I would want to put the 2 substituents. We have wedges in both cases, so we need to add both of the methyl group, which is a CH3, that and the tert-butyl group into the up position. So it's just going to be CH3 here. I like to do that to remind myself that there's a group there. We don't need to fill in the other position, but I'm going to go ahead and write it. It's good practice as you're getting going, but this is a bond line structure, so I could omit that hydrogen, and maybe that would be preferred if we were like actually at like a chemical conference or something. Okay, so the positions of the starred and the square don't change when we do a chair flip. That is, the leftmost structure's carbon is still the star, the rightmost is still the square. We go ahead and we add the axial and equatorial positions. Now the CH3 and the tert-butyl are going to flip axial to equatorial, but they're still going to be up. So we will draw this. I'm going to draw my CH3, and I always draw my CH3 to show the bond is going to the carbon. So that's why I put the H3 behind the carbon. And we add H's to either position. Sorry for running into my equilibrium arrow. So those are my 2 chair structures. I drew one, I did the chair flip, made sure I didn't move groups around, made sure that the appropriate things flipped. The flaps flip, the axial, the equatorial flip, but the upness or downness at a single carbon does not flip. So with this in mind, which is preferred at equilibrium? We assume that we're at equilibrium because I've got the equilibrium arrows drawn. And somebody would argue, well, shouldn't one equilibrium arrow be longer than the other one to show there's not, at equilibrium, there's not an equal concentration of these two? Yes, that's very good, very deep chemistry. It's not something we need to worry about right now. Okay, so which is preferred at equilibrium is the question. Well, the larger group is the tert-butyl group. So we want the one where it is equatorial. Because when it's equatorial, it cannot feel the effects of the 2 hydrogen atoms that are axial and on the same face. When it's equatorial, it's too far away. So in that case, it would be right here. Okay, so what we looked at was we practiced drawing chair structures from flat molecules. We practiced adding substituents. We considered now substituents that are small, medium, and large, small being hydrogen, large being tert-butyl isopropyl, and then medium being methyl. We then drew the structures, did the chair flips, that sort of thing, and then compared the 2 structures and said, well, which one has the big group equatorial? Maybe I didn't do a good job about this in the early part of the lecture, but when you position something equatorial, you move it away from the diaxial hydrogens that are inducing steric hindrance. So I kept emphasizing we wanted equatorial. Now, why is that? When it's axial, it feels the effect of the 2 neighboring groups, which are hydrogens in most cases, but when it's equatorial, it's just leaning too far away. It can't feel the effect. I'm going to write that down. When large groups are equatorial, those groups don't feel the effect of the diaxial groups on the same face. Now, what about the methyl group in the structure that I highlighted above? The methyl group, yes, while it does feel the effect of those 2 axial hydrogens. I'm going to erase those in a second just because I don't want people to think they need to include them when they're drawing chair structures. But does the CH3 feel the effect of those 2 hydrogens? Yes, certainly. But it's much better for a CH3 to interact with the diaxial groups, for the CH3 to deal with steric hindrance than the much larger big group, which is the terp butyl group. But it would be ideal. Okay, so I wanted to get rid of that just so that we didn't think we had to draw those. Okay, let's go on to another example I want to consider. Let's do some dashes. Let's practice some dashes. Okay, so now I've got two dashes, and in this case we have isopropyl groups, and we've kind of moved some things around. So we're going to accomplish the same thing, draw chair structures, which is preferred. Okay, we're starting to hopefully get into a rhythm of this. Okay, I really like to deal with either the leftmost or rightmost carbon. I'm going to go ahead and do this way. Put the star on the isopropyl group. If I then walk around the ring clockwise, it's the same as kind of going towards the back. That's going to put a rectangle at this position, and that corresponds to this position. So leftmost was the star, leftmost was the star. Then we walk two bonds towards the back, or in the upper, kind of going up in the bonds to move clockwise around the ring. That puts star there in square at that position. Now in this case, we do want to add our groups. But we want to make sure that we correctly attach the isopropyl in the methyl group so that they're both down. So my isopropyl group is going to be down on the star because the hydrogen would go axially or in the up position. Similarly, on the square, hydrogen goes axially in the up position, and CH3 is then in the equatorial position. Now in the chair flip, we're going to have the isopropyl group pointing down in the axial position. Remember, the up-downness of the structure remains the same. So the hydrogens are both up, which is easy to tell from the fact that our correctly drawn axial positions are both pointing downwards. Okay, so we have chair structures. Now, both of the conformations, again, I've run into my equilibrium arrow, that's my bad. But at equilibrium, which is preferred? Well, in this left structure, both groups that are not hydrogen, remember hydrogen's the smallest one, both groups that are not hydrogen are equatorial. Wonderful. We've greatly minimized our 1,3 diaxial interactions, our steric hindrance in the molecule, by positioning both groups in the equatorial position. So this structure is preferred or favored at equilibrium. So you might be thinking now, oh, well, yeah, if you've got a big group like an isopropyl or a terp butyl and a methyl group, let's put them both equatorial. Well, I couldn't in the previous example. I'm going to zip back to the previous example. Okay, so at the previous example, I can't just put the CH3 equatorial, which would certainly minimize the structure. Why is that? Well, if I put the CH3 equatorial, I would have to be swapping, and I'm going to delete this double-headed arrow in a second. I would be swapping those two positions around. And if I do that, then I have to break bonds. I have to pull off the hydrogen, pull off the methyl group, switch their positions and reconnect them. That's breaking bonds. That's chemistry. That's transformation of matter. That changes a wedge to a dash in the flat structure. So what we're doing is we're rotating carbon-carbon single bonds to give rise to new conformational isomers. So again, I said I'd delete that. So again, we're rotating carbon-carbon bonds to do conformational isomers. So that's one approach to kind of using chair structures to analyze and learn something about the molecule. chair structures are so important. Every carbohydrate, every sugar that biochemists study, for the most part, comes as six-membered rings without double bonds, which means they're going to adopt chair structures. So, for example, glucose is a really important molecule in biology. It's table sugar, but it's also the sort of piece that, when constructed in a string, will make either cellulose or starch. So cellulose, the key component of cell walls, paper, that sort of thing, a really important material. It's just a string of these chair structures. There happens to be one oxygen atom built into the chair structures, but it's still a chair structure, a really important molecule. Chair structures are just so stable that they're everywhere. Now, additionally, what I want to show you is, let's make sure I have it here still. Okay, I'm going to share with you something that's called the diamond lattice, and I've uploaded this to the to Canvas. Now, I don't expect you to actually do too much with this. You can if you want. It's supposed to be a template for you to sketch things, and you can sketch things like butane conformations, for example, or really multiple conformations. But what I want you to see is we have an array of chair structures, chair structures put on top of each other. This is called the diamond lattice. Diamond is a morphology or an arrangement of carbon. It's actually got the same elemental composition of graphite or like charcoal, for example, but it looks very different, right? And so I'm sure many of you are aware, if you put like carbon under high pressure, you do get diamonds. What happens to those carbon atoms is they form a regular arrangement of chair structures in what's called the diamond lattice. So all of these are chair structures where every vertex, every point change in direction on these bond line structures is a carbon. We know that based on what we know about chair structures. But additionally, there are no hydrogens present in a diamond lattice. There are only carbon atoms. So the axial position here is a carbon atom that's part of another chair. The equatorial position here is a carbon atom that's part of a fused chair. So you just have chairs on top of chairs everywhere, because the chair structure is so stable that if you give carbon only an opportunity to bond with itself by way of chair structures, you're going to make a very stable material, a material that's not going to want to break down or decompose or become ruptured. And as a result, you get something that's very sturdy, durable, and that's what diamond is, right? Can't scratch diamond that easily. Okay. And it's also hard to get access to such a regular arrangement of carbon, which is why you need such high pressures. Well, that'll do it for chair structures. We're going to move into another topic called chirality and introduce ourselves to concepts related to what's called stereochemistry for the rest of the module. But that's it for chair structures. Hopefully it was fun.